Okay, we're going to begin. Good evening. I'm Carrie Cronin, Assistant Library Director at York Public Library. We're pleased to welcome you to the 2025 Climate Change series titled Coastal Impacts and Resources, and tonight's kickoff program on the timely topic of sea level rise, local and regional impacts with Dean Lessard and Dr. Hannah Baranes. This series marks our fourth consecutive year of programming related to climate change in collaboration with our partners, York Ready for Climate Action and York Land Trust. Tonight's program is being recorded, and the recording will be accessible via the library's YouTube channel later this week. I will now hand things over to Marina Males, Executive Director for York Ready for Climate Action, who will introduce tonight's speakers and moderate the Q&A.
Thank you,
Welcome, Marina.
Carrie. Thank you. Yeah, York Ready for Climate Action has been so pleased to be able to be a part of these series for 4 years. We're getting a chance to talk to experts in the field, to bring people together on gloomy winter evenings over Zoom, ever since the pandemic to cover all sorts of topics related to climate change. I'm the executive director of York Ready for Climate Action. Just a peek ahead at this series, we're going to, after tonight, there'll be a Zoom in 2 weeks about offshore wind. We'll have an in-person gathering with Dan Gardoki about local birds. And then the following week, a native bird stroll out at the Center for Wildlife. We'll also be covering topics like the climate impacts on working waterfronts, how to consider sustainability for folks who are engaged in the tourism industry, and how the state is helping coastal towns adapt. We'll wrap up our series with an invasive plant removal event along with York Land Trust out at Fuller Forest Preserve. In this session on sea level rise, Hannah Baranes, Ph.D., research scientist at the Gulf of Maine Research Institute, will begin by discussing the science of sea level rise, its impacts on southern Maine, and future adaptation. She's going to address the role of climate change in the January 2024 storms that we all still remember, the projected acceleration in sea level rise later this century, and sea level rise impacts to southern Maine's coastal ecosystems. She'll share her perspective on how we as individuals and communities can prepare for future sea level rise. After we hear from Hannah, we'll hear from Dean Lessard, PE, the Town of York Engineering Department Director. He's going to provide an overview of the damage done last year at those storms that I was talking about along our beaches, and I'll be speaking about the Long Sands Beach seawall project and how the town is armoring the critical road infrastructure that's impacted by sea level rise. We're going to let our presenters speak to us, and if you have questions while they're talking, you can put any questions in the chat, and then we'll save some time at the end for those questions. I really appreciate Hannah and Dean being with us this evening. I'll briefly just go over their bios. Dr. Hannah Baranes is research scientist at the Gulf of Maine Research Institute who studies climate impacts to the coast. Her ongoing projects aim to improve near-term flood forecasting and long-term flood risk assessment, develop tools, technical guidance, and training that support local to state level decision-making, and assess the habitat quality and stability of tidal flats. Hannah is also a member of the Maine Climate Council's Scientific and Technical Subcommittee, served as a review editor on the Fifth National Climate Assessment, and co-authored the City of Boston's Regional Climate Projections Report. She has a BA in Earth Sciences from Dartmouth College and her MS and PhD in Geosciences from the University of Massachusetts at Amherst. Dean Lessard is a professional engineer in Maine with over 30 years experience in state and local government. He received his BS in civil engineering from the University of Maine at Orono. And Dean is currently the engineering director for the town of York. His responsibilities include planning and project development for the town's road and bridge capital improvement projects. Previously, you'll remember Dean was the public works director and was responsible for the town's maintenance and operations functions related to much of the town's critical infrastructure, including roads, bridges, dams, seawalls, stormwater, municipal solid waste, and recycling. So this is a person who's had his mind on sea level rise for quite some time and can really give us the details of how York is doing. But Hannah, if you wouldn't mind starting us off, please, with your presentation, and then we'll hear from Dean afterward. Thank you.
Hi, everybody. Thanks, Marina, for the great introduction and to both you and Carrie for organizing. Really looking forward to talking with you all and then to learning from you, Dean. So, okay, scariest part of the night is will the screen share work? I'll get that going. All right, I'm gonna make this full screen. Marina, can you give me a thumbs up if you're seeing the full screen version? Awesome. Okay, great. Then it's going to be easy from here. All right. So yeah, I could skip right over this because Marina gave a great intro to what I'll be talking about. So to put some pictures to it, we're going to go through what caused the unprecedented coastal flooding impacts that we experienced in 2024, the two January storms Marina mentioned, plus the additional one you all had in March. How will sea level rise affect future flooding? And then what are we going to do about it? You'll notice I left out the ecosystems piece. The agenda I put together was a little ambitious compared to the reality when I started putting the slides together, but there will be some time for Q&A, so feel free to ask about ecosystems if you're curious. Okay, so before I jump in, I want to spend a minute talking about hope. And that is because, the one thing that I think we all know about adapting to climate change is that adapting to climate change is going to require humans to act. Um, as a part of my work on the Maine Climate Council, I got to learn from this awesome scientist, Susie Arnold. If you open Maine's 4-year climate action plan, I think that's somewhere in the middle of it. There's this whole spread about the science of hope. And what I have learned from Susie is that people are more likely to act when they feel hope. And my work is to study kind of more the challenging things that are going to happen than what's going to do about it. And many people don't find that hopeful. Yet I am somebody who still feels hopeful. And kind of in being curious about why that was, what I learned from Susie is that there's science showing that hope requires agency. So, like having agency to address a problem, which includes having information, and then having a community that you're working with to address a problem. I have agency through my work, and I work with a great community of people in Maine to address these challenges. And, while I might be talking to you all about topics that you don't find hopeful, like you are here, you are all, you all showed up to this conversation. You have relationships maybe with the climate committee or the library. So I don't know where each of you are in kind of your journey towards taking action towards addressing climate change, but if, this is the beginning, this is a great start. So thanks for being here. All right. I forgot that we had that whole introduction. So this is a quick little introduction to my lab at the Gulf of Maine Research Institute, maybe just putting pictures to some of the work I do around quantifying flood risk. I do things like go up and down the coast, installing tide gauges to help with flood forecasting, doing community science with schools. I'll talk a bit about that later. Working with shellfish harvesters and scientists to understand sea level impacts to tidal flats, and then translating science to support coastal adaptation. All right, so let's jump in. So here, let's start our conversation talking about these storms. I'll focus on the January storms that had kind of unprecedented impacts in terms of coastal flooding along Maine's coastline. One thing I want to mention is that when we think about the impacts from coastal flooding, and I know this is something Dean will talk more about later, is there's impacts from inundation. So that's kind of the sustained rise in water level and just things getting wet and being underwater. And then there's the impact of having waves that pound the shoreline on top of a high water level. And that's what causes roads to break up, causes the erosion I know you all saw in the beaches in New York. And really, both of these things were at play during these events, and I will talk about why. So you'll often hear the types of storms that cause flooding here called nor'easters, and that refers to the wind direction being primarily from the northeast. Many of you might know in the two storms we had in January and the one before that in December 2023 had winds out of the southeast. And it might be a little difficult to see here, but let me see if I can get the laser pointer to work. Pointer, there we go. So in this incredible satellite image from a 2018 nor'easter you all might remember that caused a bunch of flooding in Maine too. There's this low pressure system and sitting off the coast. So the track of this storm was really kind of over the water heading up to the northeast, and that caused winds to come in from the northeast. Whereas in January, from what you can just see because I've drawn it here, the low pressure was actually sitting kind of more over land. So the storm's track was, rather than being out over the ocean, was tracking more along the coastline. Wind flows from high pressure to low pressure, and having this low pressure sitting over land rather than out over the ocean caused winds to move from southeast onshore. Um, Kind of generally, you can think about how destructive, how large waves are. It's a function of how hard the wind blows, how long the wind blows for, and something we call fetch, which is the distance the wind blows over. And you can see here that when we have winds coming out of the southeast, that third piece, the fetch, is enormous. Essentially, the next landmass you hit in some places off the Maine coast is Brazil. So that's kind of just another way of saying when these storms track more inland and winds are out of the southeast, we're much more exposed. The coastline is much more exposed. And that's particularly true for York. I get asked all the time whether sou'easters are getting more common. It was unusual to have two back to back in a single month that were both really destructive. The answer is we don't know. My lab is doing some work with scientists at the National Weather Service to try to first catalog when have all the sou'easters happened? What are some basic characteristics associated with them? And can we draw any connections between these storms that track inland with the southeast wind direction and climate? So initially, I just want to make the point that, sou'easters are not new. They've been happening, as long as we've been kind of tracking these events, we have records of them. So there was a really active decade in the 1950s. 2020s aren't over, so we can't really say so far whether they've been more common in the 2020s. This is all very preliminary work, so, stay tuned in the next few years. Okay, so to that first question, what caused the unprecedented coastal flooding impacts? We talked about destructive waves caused by southeast wind direction. We also shattered records for the total water level, so that inundation piece I was talking about. The unprecedented high water level that we saw in January, I'm going to just list them here and then I'll kind of break down each one. Number one, the storm aligned with a very high tide, and that's just kind of like a bad die roll. Number two, this is not a bad die roll. Sea level was higher than it has ever been for two reasons. One, the long-term sea level rise caused by human greenhouse gas emissions, and three, a spike in sea level during 2023 and 2024. And I'll talk more about each of these pieces. So if we take a look and kind of try to break the water level we measured down into its components, these are measurements of water level at the Portland tide gauge. So this is an instrument that's been sitting in Portland Harbor right here for over 100 years. And the green, so January 10th is right here. This is just water level versus time. January 13th is right here. The green line is showing the total measured water level. The blue line is showing the predicted tide. So that's what water level would be if there was no weather, essentially. The purple is showing the difference between the two. So that's a sort of a rough indication of what storm surge was. So just the rise in water level from onshore winds and lower pressure during the storm. What should stand out here, and this is probably not news to any of you who've been in Maine for a while, is that our tides are really big relative to storm surge. So, if you can imagine if a storm here came through at low tide, we probably wouldn't notice the storm had even happened from a water level perspective. So how severe flooding is, kind of another way of saying that, how severe flooding is for any given storm is really strongly impacted by how big the tide is on the day the storm happens to hit. And so I've just shown you the predicted tides for these few days around the storm. But if we zoom out to the entire month of January, this is showing the predicted tides. Let's see. And this box and these arrows are highlighting January 10th and January 13th. So these storms aligned with some of the highest tides of the month, and it turned out these were also actually some of the highest tides of the year. So that's kind of that unlucky die roll piece. Okay. This tide gauge is really helpful to have for a lot of reasons, not just kind of looking at a few days around the event, but we can look at the average measured water level at that tide gauge at each year since 1910. And when I look at this time series, so on the x-axis, on the x-axis, so moving from left to right is time. So you can see when this gauge was installed in 1910, and then we have measurements up through today. And then on the y-axis is the annual average sea level. So you take all the measurements of water level in a year and take an average. two things stick out here. One is that that line is going up. So that is sea level rise caused by human emissions. And sea level has risen on average about 8 inches in the last 100 years. The second thing that stands out when looking at this data is that there's the sawtooth pattern. So sea level also varies year to year as prevailing winds and currents move around. And there's this spike in so there was a spike in sea level back in 2010 that had all kinds of impacts associated with it, and we had another spike in 2023 and 2024. So that's what those last two little points are. Until about 2 months ago, I was not calling it a spike in sea level, or I wasn't calling it like a high sea level anomaly because I did not know if sea level was going to come back down. Just in December, it finally started coming down. And here's where we're at just in the last month. Specifically, we don't know what caused this spike, but in 2010, what caused the spike was just having a prevailing wind direction and that piled water up on shore and low atmospheric pressure that caused sea level to be a bit higher than average. And this has been a really interesting thing to look at because this has also had huge implications for things like harvesters having access to mud flats, like the amount of time. These fluctuations look pretty small, but I've heard harvesters say things like, I used to be able to get out on the mud flat 3 hours before low water. Now it's an hour and a half. All right. One more note about those kind of small changes in water level. So I'm talking in terms of inches right now. So I said sea level has risen 8 inches in the last 100 years. There was this 3-inch abrupt rise, and that was really one of the major. Those two things combined were one of the major drivers of the extreme flooding. I think that can be hard to picture when I'm talking in terms of inches because our tidal range is, 10 plus feet a lot of the time. So I want to get at the question of like, why do just inches of sea level rise make such a big difference in terms of the frequency that we experience flooding? So, let's see, the Zoom controls are covering my screen. I'll move those down. Okay. So another way of saying that is gradual sea level rise. So again, talking in terms of inches can rapidly increase flood frequency. And I will illustrate why. So what you're looking at on the left here, you can think of this kind of as the bell curve you might be used to that could describe something like human height. So this is a bell curve describing the height of our tides. So this is showing that, where the bars are the tallest, most of our high tides are kind of an average height. And then we have some really extreme high tides. Those are out in the right side of the tail of the distribution here. And we have some really small high tides. Right now, if I draw this line here, this could represent a flood through. So actually, this is the actual minor flooding threshold in Portland. So right now, you can see that only the most extreme high waters, so the highest high waters we experience, fall to the right of that flooding threshold. So only the very highest tides we experience cause flooding, and we only experience flooding a few times a year. So that's this, if sea level is what it was in the year 2000. If we raise sea level 1.5 feet, that's like taking this entire bell curve and shifting it to the right. So I'll show that on the next slide. Let's see. There we go. So the blue is showing what happens when we shift that whole bell curve to the right. All of a sudden, even though we haven't moved the bell curve that far, it's this much kind of fatter part of the distribution representing much more frequent high tides that are causing flooding. So even though you've only raised sea level a little bit compared to what our tidal range is, all of a sudden you go from flooding only a few times per year to flooding 1 out of every 4 days. You raise sea level 4 feet and you're flooding daily. All right, so this is kind of the part where I maybe scared the bejesus out of you all, but so what I've talked about so far is kind of the impact of the sea level rise we have seen so far on flooding as manifested by what we saw in January. So now let's talk about what we are preparing for in the future. So this is the observed rise in sea level. This is what we have actually measured. This sort of rise that we experienced from left to right is what caused the big impacts in January. My mouse kind of stopped working. There we go. Okay, I'm going to take this plot and I'm going to squish it down into the bottom left corner. So again, that black line is still showing the observed rise in sea level. And then on these same axes, if we look at what's to come, here's what we're preparing for. So this is going out to, got to keep moving the zoom controls around so I can see what's on the slides. This is going out to 2150. And you might have heard these numbers before. The state of Maine is committing to manage a foot and a half of sea level rise in 2050 and 4 feet in 2100. And this represents a kind of intermediate scenario. What I have shown here with the black dashed lines is all kind of the plausible future sea level rise scenarios that exist. And something that probably really stands out there is like, wow, that range is really wide. Like why is it so, well, two things. That range is really wide. Why is it so uncertain? And also, why does the rate accelerate so much in the future? Because we're not necessarily thinking that humanity is going to keep accelerating in terms of our emissions. So to answer that question, let's first look backwards. So if we look at what has contributed to sea level rise so far, this chart is a little bit outdated in that it's only showing through 2018. So that this is when global sea level had risen under 7 inches. A bunch of that had come from melting of mountain glaciers. So those are glaciers that sit, high up in the Andes and in the Himalayas. A lot of it had come from thermal expansion. That's just the effect of the ocean absorbing a lot of heat, and warmer ocean water takes up more space, kind of similar to the way a hot air balloon works. Hot air takes up more space. That helps the balloon float. What stands out here is that relatively little of the sea level rise we have experienced so far, or as of 2018, had come from Greenland and Antarctica, under 2 inches. And Greenland and Antarctica are these two massive ice sheets, or I guess actually 3 massive ice sheets that are sitting on top of the North and the South poles. If the entire thing's melted, sea level would rise over 200 feet. So there's an immense amount of ice locked up in those ice sheets. And so far, we've only seen about 2 inches. So what has the potential to happen in the future is that even if we were to stop emitting greenhouse gases or stop warming, these ice sheets might already be melting in a self-sustaining way. So as an example, Greenland is so cold because it sits at a really high elevation. It melts a little bit, it drops to lower elevation where it's warmer, and then it can kind of just keep melting itself without additional warming, just because it's consistently dropping to lower and lower elevation. That's something we call a positive feedback loop. Similarly, West Antarctica in particular sits in this bowl-shaped topography, and how fast that ice sheet melts has everything is related to how steep the ice cliffs are at the edges. Tall ice cliffs collapse, they become unstable, and ice moves faster into the ocean when more of it is touching the ocean. So if the ice sheet's sitting in a bowl, as you melt, the cliffs you're exposing get taller and taller. These are ice sheet instabilities that we don't quite know if we may have already triggered them, and if yes, how fast those unstable processes that cause ice sheets to collapse kick in. So the acceleration you're seeing and the uncertainty you're seeing, that's not about human warming. That's about trying to have a better understanding of how these 3 ice sheets will behave as climate warms. All right. In the last few minutes, let's talk about adapting to future sea level rise. I definitely can't pretend to be able to answer this question. I mean, the 2 things I can say for certain are reduce emissions and involve youth in whatever decisions you're making. So these are changes that are going to be accelerating in the future, extending far into the future, and we really need to be involving kind of future generations in whatever solutions we are coming up with. That being said, I'd love to talk about a little bit of the kind of near-term ongoing work that's happening in Maine to address this challenge. And first, kind of on a hopeful note, Maine is actually like quite resilient to sea level rise compared to the rest of the kind of global coastline. One phenomenon we have that really helps us out, like I've talked about a few times, are our really large tides. So when we flood, water might get really high, but 6 hours later, water drops. So it's not like water comes in and if you're in Miami and you flood, water can just sit there for days and days and days. The other thing that makes us relatively resilient compared to other places are that we don't tend to be impacted by tropical cyclones, which are called hurricanes in the North Atlantic. Um, Hurricanes, by the time they reach us, they tend to have curved offshore or they've crossed over land and had to lose some energy. And so we don't have, the same way that there can be these really damaging storms with 150 plus mile per hour winds that really threaten people's safety. We don't tend to have that issue in Portland or along the Maine coast. And what I'm showing on the right here is that our the water level for what we might call our 10-year storm or the storm that has a 10% chance of occurring annually is 8.3 feet. The rare 100, 200-year storms, they're only about a foot higher. So it's not like there's some kind of 20-foot storm surge event that could happen to us in any year. So again, just storms with lower maximum wind speeds tend to affect us. So a lot of what we're trying to do is honestly like learn how to live with water, both in terms of the way we operate today and how we plan for the future. So one really amazing thing I think is going on in Maine. We have a group of scientists who writes a report about here's what's going on in terms of climate change and its effects in Maine. That feeds into a 4-year climate action plan called Maine Won't Wait. A new one just came out. And one thing that this whole process has done is lead to this public law that requires state agencies to commit to manage, I should have said sea level rise scenarios, certain sea level rise scenarios into their laws and rules. Kind of the right side of this slide, I think someday this will be populated with, like hopefully 100 examples along the coast of Maine. But as an example, Portland just redid its zoning codes. And to me, this is sort of a really hopeful example of climate adaptation because not only does it have zoning requirements for new buildings that keeps kind of critical development out of flood prone areas, considering sea level rise. They've also addressed things like public spaces, making the city more walkable, all kinds of things that are in line with their city's comprehensive plan. So coming together to address climate change is an opportunity to kind of more broadly improve communities. And then some work that I've been involved in is this this new public law has enabled us to require consideration of sea level rise and permitting for marine oil terminals. And there's work going on throughout state agencies about updating laws and rules to consider sea level rise. Okay, then the last thing I'll talk about, and this is kind of exciting for you all. I don't know if you all know this, but you recently York is the proud new owner of a tide gauge that's measuring water levels along your coastline. So one thing that helps us live with water is being able to forecast both water level and what its impact will be. So the National Weather Service, oh man, this clicker, the slide advancer is really struggling. Let's see. There we go. The National Weather Service forecasts flooding the same way they forecast the weather. And there is a forecast point in York. The National Weather Service uses models to forecast flooding, and they can make the forecast even better when there's a tide gauge measuring water level. And your town recently invested in installing one along Shore Road. And so I'm working with the National Weather Service right now to integrate this tide gauge into their forecasting. So you all will have better flood forecasting soon. This is a slide I often show kids when I go to talk to them, but there are these flood forecasts that are like weather forecasts for flooding. So, maybe the forecasters would say water level will be 13.5 feet on Tuesday. I think I was talking to some kids in St. George, but maybe Knox County EMA would say 13.5 feet. Like, what does that mean for us? What road do I have to close? Essentially, how do I need to react to this 13.5 feet? So one thing we've been doing is using community science to try to establish this relationship between a measured water level at a tide gauge and the actual on the ground impacts so that advisories that go from the National Weather Service through EMA and to town managers, for example, can be kind of more locally specific. And this is work that we involve students in. If there are any teachers on the call, I'll just put in a plug for a whole curriculum we developed around this program. And I will end there. Thank you.
Wow, Hannah, thank you so much. I had no idea how much you were directly helping York, and so glad to hear that. And really, thank you for such good information. So we'll save our questions for Hannah for the end. Please feel free to put them in the chat if you have any that occur to you now. And Dean, I'll hand it over to you now to talk a little bit more concretely about York and what's been going on in town here.
Okay,
Thank
let
you.
me share my screen here. Thumbs up. Everyone see that screen? Excellent. Well, good evening, everyone, and thank you for coming to listen to Dr. Baranes and I. I'm going to talk a little bit about how York is adapting and living with water, particularly on Long Sands Beach. Uh, I always enjoy talking about the town of York and our projects that are going on. And so I don't know where everyone's from, but if you're not from York, we have 4 public beaches here in town. The largest one being Long Sands Beach, which is just a little over a mile and a half long. The beach is mostly hard and soft sand to the north and a cobble beach to the south. Along this, just about the whole length of the beach was a existing sloped seawall that was constructed in the 40s. There we go. So back in the late 1800s, people used the dune basically as a road to get to their cottages and hotels. Later in that century, late 1898, the Portsmouth, Kittery, and York Electric Street Railway opened for the summer. And literally the trolley tracks were laid right along the dune, right along the beach. And if you can imagine when those storms hit then, it was hours of manual labor removing rocks and debris from the tracks in order to get the trolley running again. But these transportation improvements initiated historical changes on the frontal dune on Long Sands Beach. The photo on the left, you can see the tracks and the old sand gravel road that accessed all the cottages. The one to the right, you can see the newer slope seawall, and the one at the bottom was well before the railroad was even in place. So you can see that historical transition in that area. So that slopes and concrete seawall was built to protect the new improved road, sidewalks and utilities, also the private property that had popped up along the backside of the dune along the beach. This new protective barrier helped prevent damage for the critical infrastructure and minimize the ocean flooding to the back dune and marsh area where all the residential construction was taking place. Today that taxable value for the town of York is about a third of $1 billion. So it's a substantial investment that's gone in there throughout the years. So we'll talk about some storm damage. Not just the 24 storm, but we started getting some serious damage back in Windstorm Philippe in 2017. Storm Riley in 2018, which these videos are from 2018, and Winter Storm Elliott in 2022, and obviously the high tides that we've seen on January 9th of 2024. But this is a video of those waves coming in the inundation and the power that generates in those storms. So the aftermath of just about every one of those storms was the seawall was undermined. You can see that picture on the top where it washed away feet of sand underneath the seawall and also behind it. What you can't see is the voids that it created behind the seawall. It also damaged the roads, sidewalks. We started building a bathhouse in 2017, and we moved the road in order to build that, but there was damage already to the bathhouse before the construction was even completed. So our response, I got together with our engineers and we've been working on a master plan for the Long Sands Beach, but we had to implement it quite a bit faster. So we brought the contractor in that was helping us do the sidewalk work and granite work along the road to come up with some ideas that we could armor that seawall very quickly in order to protect that million-plus investment in the bathhouse and moving of the road. And basically what we decided to do was to not tear out the existing road, but to build upon, or not tear out the existing seawall, but build upon it. And in order to fill that area underneath that had undermined, we were going to use concrete, flowable concrete, and vibrate it in there to fill those voids instead of removing all that seawall and starting to rebuild it. So the design looked like was a granite faced in order to handle the abuse of the water in the rocks and sand that was pounding on the existing seawall, backed by concrete. And this picture, you can see this was the first section we did right in front of the bathhouse. You can see that step design. Some of the neat things that we thought about was to make these steps wide enough to place a beach chair on. So what we had experienced for decades is, Long Sands Beach was a nice, great beach at low tide. And some of the higher tides, it was all covered with water and it would force people to leave. So we thought if we could build something that could also function as a respite place or place where people could gather during the short time of the absolutely high tides and then be able to walk back down on the beach after. And that part of it has been pretty successful. We've also added a lot of structure and weight to that. And basically the goal was that, the ocean's rising. We've been seeing it. But what we wanted to make sure is that when it overtopped and flooded or inundated, that when it all went away at the next low tide, that the road, sidewalk, and the private properties was still there. And from what we're seeing so far, that seems to be working pretty well. So there was quite a bit of challenges just in the construction of it. We've been at it for almost 5 years now. We've got more than about 2/3 of it completed. But of course, it's not an easy place to work in the winter. And in the summertime, the public is, on a nice warm July day, there could be 6,000 people on that beach. And there was no way that we were going to prevent them, no matter what we did, from accessing it and enjoying that opportunity in the beautiful beaches that we have. So here's a picture you can see as the seawall is under construction. We had to suspend for the summer months just because we couldn't keep the construction zone safe. There are just too many people there on a nice day. And so primarily now our construction season goes from after Labor Day to Memorial Day, and we suspend, or at least in the heavy beach area, we suspend for the summer, which has added to the length of the project, construction time, because now we're restricted to constructing the seawall in the worst days and weather of the year. So that was definitely a challenge for us, and we seem to be overcoming it. The other challenge was trying to get the seawall permitted. Maine has some substantial sand dune rules to protect the sand dunes all over the state. Fortunately, we had an existing seawall, so that allowed us to at least make an argument to the DEP that we could do something better than what was existing. But what they put the requirement on us was the replacement structure would be less damaging to the coastal sand dune, existing wildlife habitat, and the adjacent properties that were adjacent to the road. And replacing the existing structure with a structure of the same dimensions in the same location. So basically, we really can't go out any further into the beach or dune than the existing total seawall, or any higher than the existing seawall was. So what we found is there's just not a lot of studies and not a lot of information on seawalls. So couple of things that we had to look at was less damaging to adjacent properties. That was probably the easiest of all the calculations and modeling that we had to do, and for the process. But it's known that seawalls exacerbate beach erosion by the reflecting wave energy back onto the beach. And that existing seawall had been contributing to that erosion for 80 years. So in many discussions with DEP and MGS, it was decided that we need to do some kind of analysis, not just on the overtopping and the inundation, but also the wave reflection and the energy that was causing that was eroding our beaches for the last 80 years. Now that was a little bit more difficult calculation. Of course, you got wave, and we get this structure, seawall and road, as you can see here, and some of the water overtops, and that's easier to figure out and how to the steps. We could easily show that that was absorbing energy and generating less overtopping. The harder part was that reflective piece in showing that that energy coming back off the step wall was less than the existing slope seawall. So through a lot of modeling and a couple of different studies that had been done, in last one being in 2017 by Dr. Kirpin, we were able to come up with some models that would take days to run. And we were able to show that if you look here in these graphs, that the energy on the slope, which would be by the blue asterisks, was greater on that slope seawall than the red dots from the step seawall. Again, these are models and still to be proven. Those theories, hopefully in the future, as we see more storms hit the seawall. But from the models, we were showing that the slope or the step seawall was definitely reducing the energy associated with those waves. So after that, our models and done, and we presented our arguments. DEP had many different people reviewing. Actually, one of the DEP engineers actually brought in the Niles Kirpin, who was the PhD, who had done that study in 2017. The town had also hired some third-party engineers, Fuss and O'Neill and Alden Labs, to review this to make sure that everyone was in agreement that our models were as best as we could do given the situation that we were in. So, because these are just models in theory and their predictions of what the new seawall will do, part of our permit, DEP wanted a robust monitoring system, and basically to help generate more data for the future and for future projects that have to try to deal with this the wave energy. And so some of the requirements in that monitoring was a sediment survey, basically to go out and sample all the different types of materials on the beach, sand and cobble, and so that we knew exactly what was there for potential beach nourishments in the future. Also, we did extensive surveying of the existing topography of the beach, and also looked back at information that had been gathered over the years on after different storms on those elevations. And basically, through LiDAR and drones that we used to get all these elevations and show what those elevations were and are. And then in the future, we could measure these same locations to just see that the seawall is performing better and that we're not getting any more beach erosion than we would expect from the previous seawall. So we go out twice a year, and these are some of the data back from past years that we compare to, and we looked at all these different data lines, and from that we were able to create a baseline, or the lowest that we had seen previously, and that baseline is something that we'll be measuring off of in the future. So if you look at Long Sands Beach, we had 13 transects. So we focus our cross sections in these 13 locations, and we take data twice a year after the spring high tide and the fall high tide, and compare it to the previous data that we had before, to compare how the new seawall is functioning versus what had happened in the past. Some of the data, I'll flip through some of this technical stuff quickly, and if there are questions after, we can talk about it in the question and answer. But in 2000, let's see, what year was this? 12 months, 2019 through 2020. These are one of the levels that we check against is the mean sea level. And so these are the different levels for every month. And that is one exception that we have, is if for some reason we have a higher than normal mean sea level, than we had had in the past. And that would be a reason why we potentially could have some higher beach erosion than we would have been expecting. And that would prevent us from having to do some of the some beach nourishment that potentially could happen if we see that beach being eroded away. So here's some of the samples that we had taken in order to try to get grain size, color, and try to find a suitable source if for some reason that the monitoring triggers the requirement of bringing sand to our beaches in a beach nourishment project. So over the last few storms, we've been able to take some videos, especially it was kind of neat. We were able to take some videos during the construction. So if you look at this picture, the new seawall is at the bottom of the picture. And if you look to the top a little bit along the seawall, that's still the sloped old seawall. So I'll run this little video here. And you can see this, the sloped seawall absorbing some of that wave energy. And if you look at the snow on the sidewalk at the bottom of the screen, there's still snow there. The salt water isn't melting it. But if you look further up on the screen, you can see where the water is going up the slope seawall and onto the roadway, and just within 100 feet of each other. So that was a winter storm. This was later in the year. The seawall is a little bit further down, but you can see the seawall absorbing that wave. You can see there's hardly any debris here in front of the seawall, but if you look further down the road, rocks and debris all over the place. And before we started building the new seawall, we were closing Long Beach Avenue 10 to 12 times a year because of the overtopping and the danger associated with those waves being full of cobble and rocks from the beach. This is one of the first sections of the seawall by the beach, and it kind of shows or helps demonstrate that the reflective energy that it's absorbing. As that wave comes up on the seawall, it kind of cascades slowly down, whereas on the slope seawall, gravity pulls that down at a much higher rate and velocity and force. So this is where we're showing that water coming off the seawall is doing less damage to the beach than the previous seawall. Here, the seawall, it's similar to the pictures that were 2 slides ago, but there's more seawall that has been built. So it gives you a good showing of the power of those waves and just how it's absorbing that water a lot better. You look at the road, there's a lot less debris. And the road didn't have to be closed in this storm, which before would have had to be. So, the project itself, we've divided the Long Sands Beach up into 6 sections. Section 1 was that first section by the bathhouse. It was about 800 feet long. Section 2 was the next badly damaged section that went from Long Sands Road just to north of the bathhouse at the Sun and Surf restaurant. That was the next one completed. Section 3, which was south of the bathhouse to the Sun and Surf restaurant, that was completed about a year ago. Section 4, our construction just started in January of this year. They started a few weeks ago, and the last section, Section 5, will be north of the bathhouse all the way to the cul-de-sac. So here's some general information on kind of the different phases and the cost associated with this. Right now, phase 1 has been approved and obligated by FEMA. Phase 2 has been submitted. Phase 3 has been submitted, but has not been approved or obligated yet. However, it's similar to the phase 1. So we are still very hopeful that FEMA will participate with us and help us pay for this seawall. Phase 4, so 1, 2, and 3 are completed now. So those costs are no longer estimated. Those are the true costs. Phase 4 is just started. That's our estimated cost. Phase 4 was the first one. We've gone out to bid and put some restrictions on the contractor. It's a section that doesn't have much beach in front of it. So we believe we can work there in the summer. So that should expedite the completion of it. And we're predicting about a year. Once that's done, we'll move to phase 5, which will be the most difficult section because it is the highest change in elevation from beach to the sidewalk. Also, it is right in the busiest, one of the busiest parts of the beach. So we believe that Section 5 will have to restrict the summer months, which extends the construction quite a bit when you're fighting snowstorms and high tides and storms like that. But so I guess that completes my presentation, and I'd be happy to answer any questions if I can.
Yeah, thank you, Dean. Really appreciate that. The first question that we got in the chat is from Joan, and I think this question is probably for Hannah. And something that's, I imagine, on a lot of our minds. What are repercussions if there's no NOAA for state programs like GMRI? And I know that you can't necessarily predict the future, but do you have any thoughts about what you're hearing?
Yeah, so GMRI is a nonprofit. We rely on largely federal grants to do our work. So we're over half federally funded. Other of our funding comes from foundations, some state funding, and donors. So yeah, we've been had a lot of our grants threatened to be pulled, and so we'll be still a lot of uncertainty there, and we'll hopefully just be able to increase fundraising from other sources like donors and foundations.
Thank you. Thanks, Hannah. And we really appreciate your work. The next couple of questions are local questions, Dean, likely for you. First one from Deborah Etheridge. Is there a plan to repair the cliff walk?
Ah, so I believe that was just brought up at the selectmen's meeting on Monday night, and I wasn't there, so there it's in discussion. I think it probably will end up going to the voters for a vote, um, and we'll have to wait and see how that vote goes. I would imagine.
Okay. All right. And then from Mary Sue, sand levels seem to be rising. For example, tide pools behind Sun and Surf restaurant have disappeared over the last 15 to 20 years, as they have at the north end of Long Sands Beach. Please comment on the cause and whether those tide pools and thus lower sand levels would return.
Is that for me?
Yes, yes, for you, Dean.
Yes. So could you repeat that again?
Sure. So someone's noticing over the last 15 to 20 years that the level of sand seems to be higher, and therefore the tide pools are less frequent, particularly like behind the Sun and Surf restaurant. And they're wondering if what that's about and if that would change and go back down.
So some of that behind the Sun and Surf restaurant or the Anchorage Hotel, I think is where they're talking about. You mean this? Are they talking the sand on the beach, not behind? Not in
Yeah, the sand on
yeah.
the beach.
Okay. Yeah. So,
Okay.
the ocean has a funny way of moving the sand around our beach. I've seen, depending on the winds and the tides, that sand move from north to south, south to north, and it changes a couple of feet. I have noticed in the last year or so that the sand around the Sun and Surf restaurant has been higher. So in most cases, that's a good thing because that means our sand is staying there, not being moved around and going out to sea. So I'm hopeful that we'll start to see that sand coming back. And I see that the tide pools have not been like they used to be, but there's plenty to the south if they go into Long Sands Road or south of that they can still go hunt for their crabs and snails and stuff in that area. So
Okay. Thank you, Dean. Yeah, I imagine it's quite expensive for the town to replenish sand, as you were talking about having to do. So
yeah,
good news
yes.
that those levels are staying high.
Yeah, and then hopefully that's an indication that our seawall is working.
Mhm. Yeah, thank you. From Kathy K. This is also for you, Dean. Levels of tides or storms seem to be at the new construction. What happens next?
So right now we are restricted by the dune regulations that we can't make that seawall any higher. However, that seawall is designed to be scalable. If there is additional erosion below what we've experienced already, we can put another step in front of it. We could also put another step on top of the sidewalk. So that can't happen until the dune regulations would have to be changed. As I would think at some point, if the ocean continues to rise like they're predicting, that discussion will happen in the legislature, and maybe that changes, maybe it doesn't. I don't know, but we'll react one way or the other on what happens.
Okay, so it sounds like flexibility was baked into the design process.
It is scalable. We can go up and
Yeah,
go down, higher or lower.
thanks. Next question, what is being done about short sands?
So, short sands we dealt with in 2013, 14. Really, we don't have, we had the boardwalk there. We didn't really have a seawall. So we can't go right now, we can't go any higher. So what we've done is we improved the drainage down at Short Sands Village area, added the new, we got a FEMA PDM grant, the biggest the state has ever seen, and put a new 5x9 box culvert from um, the lower lying area all the way down Beach Street, outletting it onto right in front of the Union Bluff. So the thinking then and still now is that it's going to come over and it's going to flood, but the improved drainage system is handling it better. So it's not getting into the businesses, it's flooding the streets, but at the next low tide, it's gone within an hour or two. Instead of being, I mean, I think we've all seen the pictures of the canoe going down Railroad Avenue at Short Sands Beach, and that was probably 5 days after the storm. We're not experiencing that anymore with the new drainage. Within hours, we've got our grader in there pushing and loaders moving sand that has come up over the boardwalk and the water's receded.
Great, thank you. So we've got a question from Lise and Skip, and that may be all that we have time for. But let's see from Lise, what is the current project on Long Sands with low pillars and lights being installed? Is that more of a cosmetic project, or what is the estimated cost on the project, and will it be shared by FEMA? Great job to the two speakers.
Yes. So part of the Long Sands Beach master plan was to add some infrastructure there. At the time, we were thinking about Wi-Fiing the beach, and so we ran conduit in the seawall. Also, these pillars act like a little bit of a barrier, and it also helps light the steps and the sidewalk at night. As you can imagine, people are using that sidewalk or on the beach 24/7 almost. So we want to make sure that they could see that there's steps there as they walk down the sidewalk. It also provides a little bit of a barrier from that step seawall in the pedestrian area and vehicle area. We're also going to be putting some overhead lighting on just about every eighth pedestal just to help light that sidewalk and make it safe. But the answer to that is no, FEMA is not paying for that. That's part of the town's funds.
Okay. Thank you, Dean. You're really in the hot seat. We got another one if you
Okay,
feel like to
sure.
take it. So Skip says, great work, Hannah and Dean. Thank you. Two questions. Is there variation on the force of waves hitting the wall and any projection if that force will increase over time? The first question. Hannah, that might be one you could take as well.
Yeah. So I think our modeling shows that as the ocean gets higher and the waves get higher, if they do, that's where the force is. Because not every wave hits the seawall. So that's the tough thing to model it. It's only at certain times where those waves hit the seawall. Like Hannah mentioned in her presentation, at low tide, a storm surge doesn't really even impact us. Sometimes it doesn't even come to the seawall. So it's the storms that coincide with that high tide, or even like in the 2024 January, it was also an astronomically high tide, which really exacerbated the ocean level for us.
Thank you. Hannah, do you have any thoughts about the relationship between sea level rise and the power of the waves?
Yeah, I mean, waves can often be more energetic in deeper water. But again, like Dean was saying, it requires site-specific modeling to really kind of pin that down. The other thing that's going on, the energy of the waves hitting the wall will also in part depend on what happens to the sand in front of the wall. So sand is a soft surface that attenuates with a gentle slope that attenuates wave energy or reduces wave energy. And so um, force of waves on the wall will to some extent happens to what happens to that sand. And Dean kind of mentioned that looks like it might be staying, which is a good thing. And then
Oh,
to the second part of the question, like what are the projections of overflow over the wall? I mean, I think the only thing what you can say at this point is like Dean alluded to is eventually, yes, it will overflow the wall when uncertain.
right, right. All right. Thank you. We are over our time and want to be respectful of everyone's time. Thank you so much to both of you. I'm sorry for the questions we didn't get to. I'm hearing people's anxiety about what happens if federal programs cease to exist. And, I don't think we necessarily have answers for that yet, but that's certainly something we'll all be paying attention to. Um, Thank you all for sharing your evening with us, for being here and bringing such good information. You can sign up for the rest of the series on the York Public Library website, so please do that and join us for our next series in 2 weeks. Carrie, anything else to add?
I just wanted to thank all of you again for joining us, and Dean Lessard and Dr. Hannah Baranes. Thanks so much for the informative presentation. And the next program in our series will be 2 weeks from tonight on February 26th. It's another virtual program on offshore wind with Dr. Habib Dagar. So I hope to see you for that. And have a great evening, everyone.
Good night.
Take
Thanks, all.
care. Thanks again.
Bye.